At this very moment, something is happening far past the edge of the world we understand, and almost nobody has noticed. A lone machine is drifting through a region nothing built by human hands has ever touched. Until recently, scientists could only guess what it looks like out there. Every one of those guesses just got tested. For real. Here's the strange part. When this machine launched, pocket calculators were still an expensive novelty, most phones were still bolted to a kitchen wall, and cassette tapes counted as cutting edge for carrying music around. That's the era this hardware comes from, and nobody currently keeping it alive was born for years, sometimes decades. 4 watts keep it running. That's about what a small nightlight bulb uses. And on that scrap of power, it's sending back data that's quietly breaking physics models scientists have trusted for decades. This isn't just a cool science story either. What this machine found connects directly to the shield that protects everything alive on Earth from deep space radiation. And what it found about that shield isn't good news for the old textbooks. There's more. This year, engineers are running a test on this exact spacecraft that could decide how much longer it keeps talking to us at all. And there's a moment already marked on the calendar, a few months from now, that nothing humanity has ever built has reached before. Keep watching, because what this machine is finding is going to change what you think you know about empty space. I'm Dr. Bernard Kessler. If that sounds like your kind of channel, go ahead and subscribe. There's plenty more where this came from. Let's start at the beginning. Voyager 1 launched in 1977. Its job was small: swing by Jupiter, swing by Saturn, grab a few pictures, then go silent. Nobody planned for anything after that. Jupiter alone was worth the trip. The cameras caught storms bigger than Earth swirling across its clouds, and buried in the pictures was something nobody expected: a moon with active volcanoes spraying sulfur into space. First time anyone had ever confirmed a volcano anywhere except on our own planet. Then came Saturn. From Earth, its rings looked like a few solid bands. Up close, they turned out to be thousands of thin ringlets, twisted together in ways nobody had predicted either. 2 planets. 2 sets of assumptions wrong, and the spacecraft hadn't even left the solar system yet. Every extra mile it covered after that came from borrowed momentum, gravity from each planet flinging it a little faster and a little further than the last, a trick mission planners used deliberately, knowing full well it would never be repaired or refueled once it left Earth for good. By 2012, 35 years after launch, it did something nothing built by people had ever done. It crossed the outer edge of the sun's influence and slipped into the open dark between star systems. Not a nice way of putting it. A hard physical line confirmed by its own instruments. Here's where it gets weird. For decades before that crossing, physicists had built models predicting what that space should be like. Real scientists, real math, peer-reviewed work, and the models all agreed on the same basic idea: interstellar space should be calm. Thin, quiet, practically nothing happening at all. Those models weren't lazy guesses. They were built the only way anyone could build them, from a distance, using telescopes and theory, with nothing to actually check the answer against. That's an important detail, because it explains what happened next. Every one of those calculations rested on light, gathered from far away, and physics worked out on paper, never once tested against a direct reading from inside the environment itself. For most of the 20th century, that was simply the ceiling of what was possible. Nobody could do better, so nobody blamed the models for being incomplete. In 2017, an instrument on board picked up something that broke the whole picture: a signal. It didn't stop, it just kept going, spread out across a distance 10 times wider than the gap between Earth and our own sun. 9 years later, it's still going. At first, some engineers figured it had to be the spacecraft's own aging electronics acting up. A reasonable guess, given the age of the hardware. But the signal kept showing patterns tied to real events happening in the space around it, not the kind of random noise a dying part usually produces. Once that was ruled out, the harder question started. What is this, actually? For a signal that faint to even get noticed, the instrument doing the detecting had to be sensitive enough to pick out changes measured in fractions of a volt, buried inside what should have been near total electrical silence. Confirming it wasn't a fluke took repeated checks across different years, different orientations of the spacecraft, different conditions entirely, before anyone was willing to publish and say, plainly, that this was real. Researchers who studied it published their results in a major science journal. Their conclusion: interstellar space isn't the quiet, empty place the models described. It has structure, motion, detail at every size you can measure. Nobody had ever had an instrument sitting inside it before to notice. Here's why that matters beyond pure curiosity. The same boundary this spacecraft crossed also works like a shield. Our sun's constant stream of particles pushes outward and forms a bubble around the whole solar system. That bubble blocks a lot of the most dangerous radiation drifting through the galaxy before it ever gets close to Earth. It's been doing that job quietly for billions of years. If whatever's leaning on that shield from beyond turns out rowdier than anyone thought, that's not a small detail. That's a real question about how solid our protection actually is. A question nobody could even properly ask before this data existed. Some scientists studying Earth's ancient past have gone even further, wondering whether long stretches of stronger or weaker shielding over millions of years might connect to changes in radiation reaching the surface, and whether that could tie into things like mutation rates over deep time. Still speculative, still far from settled. But it's the kind of question that only makes sense to ask once you have a real reading from inside the boundary, instead of guessing from hundreds of millions of miles away. None of this science came easy. In 2023, the spacecraft nearly went silent for a completely different reason. A tiny memory chip, smaller than a coin, wore out after 46 years of constant radiation exposure. It started scrambling the data before it could be sent home. For 5 months, signals kept arriving, but they were garbage. Unreadable. Worth pointing out who was actually dealing with this. Nobody on today's team was working here in 1977. Most weren't even born yet. What they inherited was decades of old documentation and a spacecraft built by people who are mostly retired now or gone. Every fix from here on out isn't just an engineering problem, it's detective work, figuring out the intentions of a completely different generation of engineers, reading meaning into decisions nobody left behind to explain in person. Some of the original design documents exist only on paper, filed away in formats nobody uses anymore, requiring someone to physically track down a decades-old blueprint just to confirm how a single circuit was originally wired. Institutional memory, the kind that normally lives in a senior engineer's head rather than any official record, has had to be rebuilt from scratch more than once as the team turned over across 5 decades of operation. And they couldn't just drive out and swap the broken part. The spacecraft sits about 15 billion miles away. Every single test took almost 2 full days round trip. Send an instruction, wait a day for it to arrive, wait another day for a response. Look at what came back. Realize the guess was only half right. Try again. Do that for months, knowing one bad command sent across that distance could end everything, permanently, with no way to undo it. Eventually, they figured out the corrupted code couldn't be fixed where it sat, but it could be moved. They split it into pieces, relocated each one to healthier memory, and rebuilt it from a distance. Basically, remote surgery on machinery from another decade through a communication delay measured in days. By the next year, clean data was flowing again. And the very first thing it confirmed was more of that same unexplained signal from interstellar space. Now, back to the boundary itself. Old models predicted a smooth, gradual handoff at the edge of the solar system, like two currents slowly blending together. That's not what got measured. Right at that line, particles weren't cooling down calmly. They were crashing together hard enough to hit temperatures above 30,000 degrees Celsius. Some scientists have started calling that region a ring of fire, and they're not exaggerating for effect. It's a real band of superheated particles marking the very edge of everything the solar system contains. For comparison, the surface of our own sun sits at around 5,500 degrees Celsius. The edge of the solar system, a place once thought to be cold and mostly empty, is running hotter than the star sitting at the center of it. Nothing is literally burning. The heat comes from collisions, not flame. The number is real either way. This spacecraft wasn't alone in reaching that ring. Its twin crossed the same boundary 6 years later, in 2018, at a completely different spot. That gap turned out to matter a lot, because it meant two separate readings of the same barrier from two different places, and they didn't match. The thickness, the exact conditions, both varied enough to prove the boundary isn't one even, fixed shell. It flexes. It shifts with solar activity, the same activity that stirs up weather closer to home. The second spacecraft has since picked up its own version of that same signal, which is a big reason nobody's calling this a fluke anymore. The two spacecraft even took different routes on the way out. One passed through the flat plane where most planets orbit, the other went up and over. That gave scientists two genuinely different vantage points on the same boundary, not just 2 points along a similar line. Researchers comparing both data sets now describe the whole bubble around our solar system less like a smooth balloon and more like a lopsided, dented shape, wider in some directions than others. Neither spacecraft alone could have shown that. It took both, launched just 16 days apart back in 1977, still reporting home almost 50 years later. Then there's the magnetic discovery, and this one forced an even bigger rethink. Scientists assumed our sun's magnetic field and the galaxy's much larger one were two separate systems, cleanly split at the boundary. What actually got measured was field lines from both sides tangled together, exchanging energy through something called magnetic reconnection. Turns out our solar system isn't magnetically sealed off from the rest of the galaxy at all. It's connected, actively, right at the spot everyone assumed marked a clean break. That process itself isn't new to physicists. It's the same basic mechanism behind solar flares and behind the auroras that light up the sky near Earth's poles. What's new is finding it way out at the far edge of the solar system, in an environment nobody thought had enough energy to sustain it. Every existing model of how radiation moves around our neighborhood assumed a mostly sealed system with the occasional small leak. What this data suggests instead is a boundary that behaves more like a loose curtain than a solid wall, constantly trading energy with whatever's on the other side. Researchers who spend their careers forecasting space weather closer to home, the kind that can knock out satellites or overload power grids during a bad solar storm, are now having to factor in a boundary 60 times further from the sun than anything they previously modeled in detail. It's not that everything they knew was wrong. It's that a piece of the system they treated as a closed loop turns out to have a door in it, and nobody had measured how often that door actually opens. Let's talk about right now. Every one of the spacecraft's 3 power generators runs on decaying plutonium, and that output drops by about 4 watts a year. It started around 470 watts at launch. Today it sits closer to 250. This spring, engineers powered down one of the 2 remaining working instruments, not because it broke, but to buy time before an automatic shutdown forced their hand under worse conditions. Right now, there's an experimental fix underway, rerouting how electricity moves through the spacecraft's remaining systems to squeeze out capacity that's currently going to waste. They tried it first on the sister spacecraft, which has a bit more power to spare. If that worked, the same attempt gets cleared for this one, no earlier than this month. If it succeeds, that instrument powered down in spring could switch back on. Out of the 10 separate instruments this spacecraft originally carried, 7 have already been switched off over the years, one after another, in a carefully planned order designed to squeeze the most possible science out of a shrinking budget of electricity. Every one of those decisions was final. There's no manual override sitting somewhere waiting to flip a dead instrument back on once its power gets cut. Each shutdown closes a door permanently, and the team making that call knows it going in. There's a reason there's any spare capacity left to find at all. Engineers back in the 1970s built in generous safety margins, standard practice for a mission this risky at the time. They had no way of knowing that decades later, a completely different team would need to squeeze every last bit out of that same margin just to keep basic systems running. What counted as careful, conservative design back then reads today almost like a gift left behind for whoever inherited the problem. Worth asking why anyone keeps fighting this hard for a machine this old, instead of just letting it go quiet. Missions that reach this far out cost a fortune and take a decade or more to arrive anywhere. Set against newer proposals that deliver results in a few years instead of a few decades, distant missions almost always lose that funding fight before it starts. This spacecraft isn't competing for that money anymore. It's already out there, already sending back information nothing else can currently replace, for a fraction of what building something new would cost. That's the real reason nobody wants to let it go. There have been proposals for a proper successor, something built from scratch with modern sensors made specifically for these conditions, instead of 1970s hardware doing a job it was never designed for. Engineers have sketched out concepts for a probe that could reach interstellar space far faster than this one did, carrying instruments tuned exactly for the kind of turbulence this mission stumbled into, almost by accident. Getting a concept like that from paper to launch pad typically takes the better part of a decade on its own, even once money is approved, before the actual multi-decade flight even begins. None of those plans currently has funding or a launch date. Until one does, this aging spacecraft remains the only active source we have for understanding the space directly outside our front door. Power isn't the only thing that's needed saving. This spacecraft steers itself with tiny bursts from small thrusters, keeping its dish pointed at Earth with precision measured in fractions of a degree. The main set of thrusters started building up buildup that threatened to block their fuel lines shut, with engineers estimating maybe a year or 2 before failure. Instead of waiting, in 2025, the team switched on a backup set that had been considered dead since 2004. 21 years of assumed silence, reversed by a command sequence nobody was fully sure would work. What made that attempt especially nerve-wracking wasn't just the age of the hardware. It was that nobody could test it small first. The fuel lines feeding those backup thrusters had sat untouched for 2 decades, with no way to check remotely for damage or blockage. It was full commitment on the very first try, based on simulations and best guesses, with 0 confirmation, until results came back a day and a half later. When the data showed the thrusters had fired exactly as commanded, nobody at Mission Control treated it as routine. It was treated as one of the more unlikely wins of this whole extended mission. If those backup thrusters hadn't responded, the fallback plan involved switching to the primary set anyway and simply accepting a shorter remaining lifespan, monitoring fuel line pressure closely and hoping the residue buildup held off longer than engineers feared. Nobody wanted to test that fallback in practice. The fact that they never had to remains one of the quieter pieces of good luck in this entire 50-year run. And no matter how that power test goes, there's a fixed point still ahead. This November, the spacecraft crosses a distance from Earth measured not in miles, but in light time. A full day. Send it a message that day, and a reply takes 2 full days to come back. Nothing humanity has ever built has been that far away while still talking to us. For scale, sunlight takes a little over 8 minutes to reach Earth. This spacecraft will be far enough out that the same kind of signal needs a full 24 hours to make that trip, something like 170 times further in terms of travel time than the gap between us and our own star. Nothing changes the moment that milestone hits. No dramatic switch flips. It just marks, permanently, a distance nothing human-made has ever managed to close before. Eventually, sometime in the next 10 years or so, the power will drop below what even one instrument needs, and it'll stop transmitting for good. When that happens, nothing slows it down. No air out there to create drag. Nothing nearby heavy enough to knock it off its path. It just keeps drifting in a straight line, forever, carrying a small gold disc bolted to its side. 55 languages of greetings. The sound of rain. Ocean waves. Human laughter. 90 minutes of music pulled from across human history. A map showing exactly where it came from. A small group spent months arguing over what belonged on that disc, knowing whatever they chose would represent the entire species with no chance for a second draft. They picked a classical piece and a rock and roll song, a wedding tune from South America, drumming from West Africa, a mother's first words to her newborn, recorded just for this. They left out war, they left out disease and conflict entirely. Not because those things aren't part of being human, but because the group decided this disc should carry an invitation, not a warning. Instructions on the cover, based on nothing but basic physics and the positions of nearby stars, are meant to let whoever finds it work out where Earth is, and roughly when this was sent, without needing to share a single word of language. The committee behind it worked under a brutal deadline, pulling material together in a matter of weeks rather than the years such a decision might normally deserve. They fielded suggestions from scientists, musicians, and diplomats, argued over which single sound could possibly stand in for an entire species, and in the end accepted that no choice would ever feel complete. What made the final cut wasn't meant to be the best of everything humanity had produced. It was meant to be honest enough that whoever eventually found it would recognize, immediately, that real curiosity had built it. One of the people who helped build that disc once compared it to a message sealed in a bottle and dropped into an ocean with no shore. Long after our sun swells up and swallows the orbit Earth sits in today, that record keeps moving. Long after every city we've ever built has crumbled to dust, it keeps moving. Space out where this spacecraft is drifting doesn't behave the way most people picture it. It isn't heading toward another star system. There's no destination programmed in, only a direction. And the nearest star along that path is still so far off it's basically meaningless to measure in human lifetimes. What it's sampling right now is thought to stretch on for an enormous distance before it gives way to whatever bubble surrounds the next star over. A stretch disturbed now and then by exactly the kind of turbulence this mission has been recording since 2017. Every star that gives off a stellar wind carves out its own version of this bubble. Astronomers call them astrospheres, and telescopes have actually spotted the glowing edges of some of them around other stars from a distance, sometimes shaped like a bow wave pushed forward as that star moves through the galaxy. What none of those distant views can do is tell you what conditions are actually like inside the boundary itself. That kind of detail only comes from physically being there, and right now, for any star including our own, that's happened exactly once. Comparing our own bubble to those distant ones is still mostly guesswork stitched together from indirect signals, brightness patterns, and faint glows captured across enormous distances. Every one of those comparisons would benefit enormously from a second direct sample, ideally from a star system built differently than ours. But no mission capable of that kind of trip currently exists, funded or otherwise. Until something changes, our solar system's boundary remains the only one anyone has ever measured from the inside. One loose thread worth mentioning before we wrap up. Researchers still don't know exactly what's causing that 9-year signal. Two explanations are still on the table. One is a fairly normal kind of plasma vibration, real, but something existing physics already has room for. The other possibility involves a different kind of background noise entirely, one tied to how dense and warm the plasma actually is out there, and if that's what's actually happening, the standard picture of density and temperature out there needs a real overhaul, not a footnote. Telling the two apart isn't something one aging, dying instrument can settle alone. It would take a dedicated new mission built specifically to measure this environment properly, and nothing like that currently exists or has funding behind it. So the question stays open, gathering more supporting data every year without anyone able to close the case. Part of why this is so hard to pin down is that the instrument doing the listening was never built for this job. It was designed in the 1970s to study conditions much closer to the outer planets, never meant to spend decades picking up a faint signal in the near-total silence of interstellar space. Every reading it produces now is squeezed out of hardware running well outside what it was originally built for, on parts that have never once been serviced or replaced. That the data holds up at all, let alone precisely enough to spark real scientific disagreement, says as much about how well 1970s engineers built things as it does about the mystery itself. There's a real cost to that uncertainty lingering unresolved. Every year this question stays open is another year of published papers hedging their language. Another round of conference talks presenting both possibilities side by side rather than a settled answer. Scientific fields can live with open questions indefinitely, but this particular one is running against a clock nobody controls, because the one instrument capable of adding more evidence is losing power every single year, with no guarantee it survives long enough to ever tip the argument one way or the other. Step back and look at the whole shape of this. A machine given 5 years turned into one still working after nearly 50. A part that failed after almost half a century got rebuilt from 15 billion miles away instead of thrown away. Thrusters written off for 2 decades fired again on command. A boundary predicted to be gentle turned out to be a 30,000-degree collision zone. 2 magnetic systems assumed to be separate turned out to be talking to each other. And through every single one of those moments, running on less power than it takes to light a small bulb, it kept sending home information that made the universe look stranger than the textbooks claimed. This isn't really a story about old hardware refusing to quit. It's a story about how little we still know about the space right outside our own front door, and about a machine that, for now, is still the only thing out there able to tell us anything about it. Nobody at Mission Control claims to know how many more rounds of this are left, or how many more times a supposedly dead part gets talked back into working. They're just running the numbers, sending the commands and waiting out the silence to find out. There's something worth sitting with here. A piece of hardware built during the disco era, running on less computing power than a basic calculator, is currently the single best source humanity has for understanding the region right outside our solar system. Every bigger, newer, more expensive thing we've ever built has stayed closer to home. This one didn't, and everything it's found since raises more questions than it answers. Usually, that's a sign a field of science is working exactly the way it's supposed to. It's worth remembering, too, that almost none of this was inevitable. A slightly different launch window, a slightly worse component, one failed course correction decades ago, and this entire body of knowledge simply wouldn't exist. Nobody in 1977 was betting on a 50-year mission. The people who built this thing were solving a 4-year problem as carefully as they knew how. And the fact that their careful, unglamorous engineering choices are still paying off half a century later says something about how good work tends to outlast the ambitions behind it. When that last signal finally does arrive, sometime in the next decade, it won't be a clean ending. No shutdown ceremony. No final message prepared in advance. Power will just drop below what's needed, the dish will keep pointing at a planet it can no longer reach, and the spacecraft will keep moving anyway, golden record still bolted in place. Unanswered questions trailing behind it into a part of the galaxy no living person will ever explore directly. Whatever comes after that silence, whether it's a proper successor decades from now, or nothing at all for a very long time, this machine will have already done something no plan on paper ever accounted for. It kept going long enough to prove how little we actually knew. If you'd rather follow this mission as it actually happens, instead of hearing about it weeks later, subscribing and turning notifications on is how you do that. We'll check back in the moment there's news on the power test. And I'd genuinely like to know, out of everything in this video, what part stuck with you the most? Tell me in the comments. It shapes what gets covered here next. Thanks for watching.